Suppose you're asked to graph the function f of x equals x cubed minus 3x squared minus 9x. So since this is cube, I hope you have an idea that the graph will somehow looks like this graph. Now, since we're interested in the maximum and the minimum points where the slope of the tangent line is 0, it means that the first derivative is 0. So we have to get the first derivative of the function. So getting the first derivative of this function, f prime x, that will give us 3x squared minus 6x minus 9. And factoring 3 out will give us x squared minus 2x minus 3. Further, we may factor the 1 inside the parentheses, so that is x minus 3 and x plus 1. Now, since we're interested again in the maximum and the minimum points where the slope of the tangent line or the derivative is 0, then we have to set this to 0. And that will give us values of x, which are, so solving for x, so x minus 3 is 0, x plus 1 is also 0, so x is 3, and x is negative 1. These are what we call the critical points. The critical points are simply the values of the x-axis where the maximum and the minimum points are. To show this, suppose this is negative 1 and suppose this is 3. Somewhere in negative 1 will be our maximum or minimum points. And somewhere in 3 will be also a maximum and minimum points. Now, there's what we call as the first derivative test. The first derivative test determines whether the graph of that function is increasing or decreasing at a certain interval. Since this is negative 1, it will determine whether from negative infinity up to this point, is the graph increasing or decreasing? Up to this point, is the graph increasing or decreasing? And how about this point? So it simply partitions the graph into parts in which the divisions are the critical points. So let's determine this first. From x in which the x is less than negative 1. So let's try x equals negative 2. Again, any value that's less than negative 1. We're going to substitute that negative 2 to the first derivative. So substituting negative 2, we have 3 negative 2 squared minus 6 times negative 2 minus 9. And that is 12 plus 12 minus 9. That's 15. And that's positive. So since this is positive, or in other words, the derivative is positive at this interval, the derivative at this interval is positive, or in other words, the slope of the tangent line at this interval is positive, then we know that the graph will be increasing from negative infinity up to negative 1. Okay? Now, how about at this interval? From negative 1 up to 3. So we're going to substitute any value of x that's between negative 1 to 3. Let's take 0. Substitute 0 again on the first derivative here. So that will be 3 times 0 squared minus 6 times 0 minus 9. Or simply 0 minus 9. So that is negative 9. So that's negative. So meaning, the slope of the tangent line at this interval is negative. That indicates that the graph is decreasing at this interval. Now, how about at this interval from 3 onwards? So, x greater than 3. So let's take any value that's greater than 3. Suppose 5. Substitute 5 on the first derivative. So we have 3, 5 squared minus 6 times 5 minus 9. So that is 75 minus 30 minus 9. So that is 36. So that is still positive. So since this is positive, that indicates that at this interval, the slope of the tangent line is positive, indicating that the graph is increasing. So we know that the graph will increase here. Suppose this is your graph. And decrease here. And then it will increase again. So the first derivative tells us that if the first derivative is positive at this interval, then the graph is decreasing at that interval. And this is shown by this and this interval. Then, on the other hand, if the first derivative is negative at this interval, then the graph is decreasing on that interval. So this is negative, so at this interval, negative 1 to 3, the graph is decreasing. If we're interested to find the maximum and the minimum point, all we have to do is to substitute these critical points to the original equation. So let's substitute if x is negative 1, so f of negative 1 will be, so that's negative 1 cubed minus 3 times negative 1 squared minus 9 negative 1. So that's negative 1 minus 3 plus 9. So that is 5. So meaning we have a point which is negative 1 and 5. So at this negative 1, we know that this point is negative 1, 5. And we know that that is a maximum point. For the minimum point, surely it will be coming from this 3. So substituting x equals 3. So f of 3, we have 3 cubed minus 3 squared minus 9 times 3. And that is 27 minus 27 minus 27. That's negative 27. So we have a point now which is 3, negative 27. So this point now is 3, negative 27. So the minimum point is 3, negative 27. And since this part is not the absolute maximum, since there are still points higher than that, then this point is a relative maximum. And 3, negative 27 is not absolute since there are still points that is lower than that. So this point is also a relative minimum. Next, suppose we are interested on what we call the inflection point. It's somewhere here. The point of inflection again is the part of the curve when the tangent line changes its direction from clockwise to counterclockwise or counterclockwise to clockwise. So to find that point of inflection, we have to get what we call the second derivative. The second derivative is simply the derivative of the first derivative. So since our first derivative is 3x squared minus 6x minus 9, getting its derivative again, we have the second derivative, represented by f double prime of x. So the derivative of this is 6x minus 6. And setting this to 0, we have 6x minus 6. Solving for x will transpose 6 on the other side. So that is x equals 1. Now it tells us that this is 1. This point here is the point of inflection. We may substitute 1 on the original function to get ordered pair of that point. So that is f of 1. So 1 cubed minus 3, 1 squared minus 9 times x. We have 1 minus 3 minus 9. So that's 1 minus 12, we have negative 11. So this point is 1, negative 11, which is the point of inflection. Now, we have what we call the second derivative test. the second derivative test works like the first derivative test. Wherein from the inflection point, you're going to determine now some property of the graph from negative infinity up to 1 and from 1 up to positive infinity. Using 1 here as the partition of the graph, so if x now is less than 1, let's take a value that's less than 1. The easiest one is 0. Substitute that on the second derivative. So that's 6 times 0 minus 6. So that's negative 6. And if that's greater than 1, then let's substitute x greater than 1, let's say 2. So substituting 2 on the second derivative, so that's 6 times 2 minus 6. So that is 6. So that's positive. Now, what does this tells us? This tells us that if the second derivative is positive, then on that interval, it's concave upwards. And if it's negative, then it's concave downwards. Meaning, at this interval less than 1, meaning all the parts of the graph less than 1 up to here, to this part, up to the inflection point, the graph is concave downwards, meaning its shape looks like this. So that's why on this part of the graph, up to 1, the graph is concave downwards. And after 1, the graph changes its shape to being concave upwards. So we can see here that the point of inflection does not only tells us the change in the direction of the tangent line, but it also gives us the change in the shape of the graph. So from concave downwards, from negative infinity up to 1, 1 up to infinity gives us a concave upward of the graph.